Hello everybody, getting ready to do lesson 10.3 part 1 of pre-calculus math today. And for today's lesson you got 14 points that will go on to your notebook guide, have that out. And 32 points will go on to your class worksheet, have those out, name, date, period. Onliners and homeschoolers, put your due date there. Teachers, students, we go right into our bell work for the day. Evaluate the expression without using a calculator. Cosine 480 and sine 690. Give your students about 3 minutes. Teachers, they should have that. Welcome back, everybody. And for number 67, cosine 480 degrees is actually cosine 120 degrees, which equals -1/2 is what cosine 480 is. You subtract 2 pi from that and you end up with 120, which comes out to being cosine 120 becomes -1/2 for cosine 120. And then down here for sine 690 you do the same thing here. It'd be the same thing as sine 330 here. You subtract 2 pi radians from this and you come up with sine 330 degrees, which equals the same thing, funny enough, -1/2. Into today's lesson, we start right off here with the cross product. Many applications in physics, engineering, and geometry involve finding a vector space that is orthogonal to two given vectors. In this section, you will study a product that will yield such a vector. It is called the cross product, and it is most conveniently defined and calculated using the standard unit vector form. Okay, so the definition of cross product of two vectors in space. Let u equals u1i plus u2j plus u3k and v equal v1i plus v2j plus v3k be vectors in space. These are two vectors in space. The cross product of u and v is the vector u times v, which is u2v3 minus u3v2i minus u1v3 minus u3v1j plus u1v2 minus u2v1k. So that's quite a clutch there of information. Make sure this goes in your notebook, page 1. So having that, it is important to note that this definition applies only to three-dimensional vectors. The cross product is not defined for two-dimensional vectors, if you were thinking. A convenient way to calculate u times v is to use the following determinant form with cofactor expansion, meaning this 3×3 determinant form is used simply to help remember the formula for the cross product. It is technically not a determinant because the entries of the corresponding matrix are not all real numbers. But we're going to use it anyways, just as a teaching tool. So u times v will equal the same thing here. We have a matrix here. Underneath I, you have ui. You have u1 v1, and underneath j you got u2 v2, and underneath k you got u3 v3. And then so put u in second row here. So you put u in second row and then you put v in the third row. So just remember that. This goes in your notebook, page 2, 10.3 part 1. Just remember that. That should be easy on your notebook guide if you have one. Okay, so now to figure out what I is, again, you cross this column out, you cross this top row out, and then you multiply by that, by I, do the same thing over here by j, multiply this, and then subtract that. Remember, this goes back to chapter 7, times j, and then for k here, you obliterate that row, you obliterate this column, u1 v2 minus v1 u2 times k. So it's just like chapter 7 again, and then this is what you end up with, u2 v3, etc. Like these, you end up with these matrices here. And then this is how that was derived, actually, was by this concept here. Note the minus sign in front of the j component. So the j component here, you have this minus sign here. Recall from section 7.7 that each of the three 2x2 determinants can be evaluated by using the following pattern. So we do have a negative sign here. What about that? So we have a1, b2, a2, b1. So it's a1, b2 minus a2, b1. Remember that? So here's an example of it. So we have 2 times negative 1 minus 3 times 4, or 4 times 3, which equals negative 4. So that's really where that negative sign comes from. It's kind of the middle object of that. So finding cross products, given u equals I plus 2j plus k and v equals 3i plus j plus 2k, find each cross product. So here's our u, is right here, I plus 2j plus k, then v is 3i plus j plus 2k. Because of this up here, u and v. So let's find u times v now, u times v. Okay, so to do that, u times v, we have ijk. Ijk is our columns here. And then our rows here are 1, 2, 1. So 1, 2, 1 is up here for our u. And then our v here is 3, 1, 2, which is this up here. So we end up with this. So we end up with 2 times 2 minus 1 times 1, I, minus 1 times 2 minus 3 times 1, j, plus 1 times 1 minus 3 times 2, k. And that was that one. So this, when you add those together, you should have this sums here, 4 minus 1i, minus 2 minus 3j, plus 1 minus 6k. And then when you combine like terms here, we have 3i plus j. You have a negative 1 minus a negative 1 is positive j. And then minus a 5k. So that's that cross product there. So now what about b? V times u. Instead of u times v, now we're going to go v times u. So v times u, here is our array here, ijk. 3, 1, 2, 3, 1, 2. V here is our top row here. And then u would be our bottom row, would be 1, 2, 1. We go down here. And we do the same kind of process. So we end up with 1 times 1 minus 2 times 2i, minus 3 times 1 minus 1 times 2j, plus 3 times 2 minus 1 times 1k. Having that operation done, this will give us 1 minus 4i minus 3 minus 2j plus 6 minus 1k, and that comes out to negative 3i minus j plus 5k over here. So note that this result is the negative of that in part A. So we have a negative out here in front, whereas in part A, there was no negative there. So now let's try C here. So we have V times V. So V, each one of these times, we have this times this, okay? So V times V, we got 3, 1, 2, 3, 1, 2. And that comes out to being 0. By the time you do the same cross multiplication there and you subtract them from each other, you end up at 0. Okay, so let's try one. U times V. Find U times V and show that it is orthogonal to both U and V. So we have U up here, and then we have V here, and they want us to do U times V. This is yours down here, students. So u times v, here's our setup. Here's our rows here. U is 6, 2, 1. V is 1, 3, negative 2. And then this ends up, by the time you do your calculations here, I'm going to let you do that. This is your answer sheet. If you want to attach a page to this, students, you can. But you end up here with negative 7i plus 13j plus 16k. And this can be summarized here in component form as negative 7, 13, and 16. So this is the vector in component form. So we have that, and then u times v, we have 6, 2, 1, which equals, see here, u times v times u. So u times v is this, and then we multiply it times u, and then we get 0. And then we do it again, u times v, and we get 0 there as well. So that proves that it is orthogonal, that u and v, both u and v are orthogonal. The results obtained in example 1 suggest some interesting algebraic properties of the cross product. For instance, u times v equals the negative of v times u, and v times v equals 0. These properties and several others are summarized in the following list. Algebraic properties of the cross product. So let u and v and w be vectors in space, and let c be a scalar. So we have u times v equals the negative of v times u. We change places here, and we get the negative of that. And then u times the quantity v plus w will equal u times v plus u times w. And then 3 is c times u times v equals cu times v will equal u times cv. So these are equal quantities here. And then u times 0 will equal 0 times u, which will equal 0. And then u times u will equal 0. That's a good one there. And then u times the quantity v times w will equal u times v times w. So these are the algebraic properties of the cross product. Geometric properties of the cross product. The first property listed on the preceding page indicates that the cross product is not commutative. In particular, this property indicates that the vectors u times v and v times u have equal lengths but opposite directions. That is really a great fact. There are equal lengths but opposite directions. The following list gives some other geometric properties of the cross product of two vectors. Geometric properties of the cross product. Let u and v be non-zero vectors in space, and let theta be the angle between u and v. So 1, u times v is orthogonal to both u and v. And then the directed vector u times v equals the directed u times the directed v sine theta. And then u times v will equal 0 if and only if u and v are scalar multiples of each other. Only if u and v are scalar multiples of each other. And then the directed vector of u times v equals the area of a parallelogram having u and v as adjacent sides. So this can be used actually to find area of a parallelogram. Both u and v times u are perpendicular to the plane determined by u and v. One way to remember the orientations of the vectors u, v, and u times v is to compare them with the unit vectors I, j, and k equals I times j as shown. So here we are. Here k equals I times j, which is this here. Then we have I this way, and then J this way. Everything is a 90 here. So the orientations of the vectors U, V, and U times V is to compare them with the unit vectors I, J, and K equals I times J. So K here equals I times J, and you get this right there. The three vectors, U, V, and U times V, form a right-handed system. So we have what's this called a right-handed system, which is what? We're going to find out. Using the cross product, find a unit vector that is orthogonal to both U equals 3I minus 4J plus K and V equals negative 3I plus 6J. So the cross product of U times V here, U times V here, U times V here, the cross product as shown is orthogonal to both U and V. So this is the orthogonality here to both U and V. And this is Y here. This is the analytical way. U times V here. We have our rows here and we have our columns. This will come out to being negative 6I minus 3J plus 6K. And that is this segment here. That is this vector here. When you multiply these two together, you get this. Because the directed vector U times V equals, and we go into this, we put negative 6 squared plus negative 3 squared plus 6 squared. Then we take the square root of that and we get square root of 81, which equals 9. So that equals 9. A unit vector orthogonal to both U and V is U times V over the directed vector of U times V, which will equal the negative 2/3 I minus 1/3 J plus 2/3 K. So this will be the unit vector orthogonal to both U and V here. You get this array here. So find a unit vector orthogonal to U and V. Here's our U and V. So now we're going to find a vector that's orthogonal to it. So we have U times V, I, J, and K. We have 3, 1, 0, then 0, 1, 1 for V here. And then when we do our cross multiplication, we come up with I minus 3J plus 3K. And then our directed vector will be U times V will come out to radical 19. So our unit vector will equal U times V over the directed vector of U times V will equal 1 over radical 19 times I minus 3J plus 3K. This comes out to be in radical 19. When we rationalize our denominator here, we have radical 19 over 19 times 1, negative 3, and 3. So this would be a unit vector that would be orthogonal to U and V. And that is 10.3 part 1, pre-calculus math. My email is animatedpowerpointmathvideo@aol.com. Email me for materials or questions. Thank you very much.